Um, we now start Module 4 of my course, Random Processes and Kalman Filtering. In Module 2, we talked about random processes. In Module 3, we talked about linear systems, just deterministic linear systems. Now in Module 4, we talk about random processes being the inputs to linear systems, and we want to see what the output looks like. In everything we're going to talk about, every input signal, every input random process in this module, we're going to assume is wide sense stationary. So that's one big assumption about this whole module. And in general, to talk about random processes through linear systems, we could talk about like the time domain analysis, and we could talk about, or we could talk about steady state analysis like frequency domain analysis. And we're going to do that. We're going to sort of look at these things both ways, but we're going to start with the steady state analysis, the more frequency domain type analysis. In these cases where we run random processes through linear systems. And for that, because we're looking at steady state, we have to assume the system is stable when we're doing the steady state analysis. And when we looked at linear systems, we had this relationship in the Fourier domain, that the output equals this product of, call it the transfer function, and the input, all being Fourier transforms. And a feature of the Fourier transform, like the Laplace transform, if you have a product like this in the Fourier domain, it translates into convolution in the time domain. So that the output in steady state, and now this X means steady state output, not the true overall output, only in steady state. It's this convolution, and since convolution is commutative, we could express it either way. And these relationships even apply to non-causal systems. If it is a causal system, meaning this G is 0 for t less than 0, then it's these convolutions. You'll notice it's different limits on the integrals. So this is the steady state output. This F is the input. It's a random process. And we're going to concentrate on this relationship here, this convolution here, to do some analysis. Here it is repeated. Since we're now talking about random processes, we can't really evaluate the integral directly. This output is a random process. So we look at the common things like the mean, the autocorrelation function, the mean square, the power spectral density. Those are the big things we're going to look at. So let's look at the mean first. Well, the mean of X means this expectation. Put this integral in that expectation. And now because integration is a linear process and the limits of the integral don't involve anything random, we can move the expectation operator inside the integral. And this G here is not random. The system is not random. The input is random. So the expectation just amounts to taking the expectation of the input, and we said it's wide sense stationary, which means that expectation is just a constant, whatever the mean of the input is. So we have this relationship, so we could pull that mean out, and you're left with this. And this, by the way, is the Fourier transform with the argument of 0. Here, prove it here. If I put in omega equals 0 here, you know, this Fourier transform is a function of omega. omega equals 0, I'm just left with this integral here. But if this g is causal, that lower limit becomes 0 instead of minus infinity, which means it just becomes the Laplace transform evaluated at s equals j omega, so that this g of 0 up here is just a good old Laplace transform transfer function evaluated at s equals 0 or j omega equals 0, omega equals 0. Anyway, it's a nice, simple relationship finding output mean and steady state. What about the autocorrelation function? By definition, it meant the expectation of these two random processes, the product of two random processes. Here's those functional relationships again. It's these two integrals. I'll use two different variables of integration now because I'm going to combine them, make this product one double integral, and again move the expectation operator inside the integral. And the expectation of this guy, because we said the input is wide-sense stationary, that's just the autocorrelation function with the argument being the difference between these two arguments. So T2 minus V minus this quantity. And you'll see that you have a T2 minus T1 here. I could just call that tau, the time difference, which means the output autocorrelation function in steady state is wide-sense stationary if the input's wide-sense. Power spectral density. Remember, by definition, power spectral density was the Fourier transform of the autocorrelation function, which means this is the Fourier transform. Put what that RX autocorrelation function is from the previous chart in there, where here, and then change the order of integration. So the inner integral is over T, this guy here. Let's look at this guy for a minute. Just that guy. I'll change a variable here so that the argument becomes this thing. I'll make tau equal T plus U minus V. And now I can pull out a minus J omega minus U plus V. Means this, and what's left is that integral just is the power spectral density of the input. Now I'll put this back in here. So the power spectral density output is now this integral. And I can split this double integral into two integrals. And each one of these is just that transfer function with these two different arguments, j omega and minus 2. And this is the same if g is real, which we're going to assume. This last line is the same as that line. And anyway, that's the same relationship we had even with deterministics. Now that relationship works with random processes. So we have a way to relate or find the output power spectral density knowing the input. And one last thing, the mean square here. Well, the autocorrelation function is this Fourier transform of the inverse Fourier transform of the power spectral density. And remember that the mean square is just the autocorrelation function evaluating 0, arguing 0. Put a 0 in here, that becomes a 1. And you have that. So that there's a couple ways to find the mean square. One is to find the autocorrelation function. There's an argument of 0. Another way is to evaluate this integral, integrate the power spectral density. This picture just is trying to show the input is wide sense stationary. The output is only wide sense stationary in steady state. It's going to have a transient phase, not necessarily wide sense stationary. So here's kind of a summary of those key relationships. You can find the output mean, the output power spectral density, the output autocorrelation function, and the mean square value, either from the autocorrelation function or from the power spectral density. And by a change of variables, I can go from here to here. We're not going to use this integral directly, but it's going to be used to derive some formulas that we will use. This requires complex functions of a complex variable. And one last thing. If I just scale up the input power spectral density, I go from S of F to A, the constant A times S of F. Then the output power spectral density, the output autocorrelation function, and the output mean square are all scaled by the same constant. So I'll save the example for another video. Now we have all the formulas for steady state analysis.